So there's actually this explanation. Okay, so if we increase, if the partial sum, which we increase from P1 and then 3, 5, 7, we are going to get like approximating the sign x. Why there is only the odd number? Because in the sign x, if we try to build up the Maclaurin series, we are going to see that that is the necessary numbers, which is the odd numbers, that is going to be built up as a important numbers. Okay, so I will give you some example. Okay. So we have the functions sin x. For the Maclaurin, we're going to take at x equals 0 to get the coefficient. Okay. And since the coefficient will be relatively between 0, 1, or negative 1, okay, as in trigonometry, right? If you have 0, so we works this maybe up until 3 or 4, we are going to see the pattern. You will see that we have 0, 1, 0, negative 1, which means that one or another, there will be either even number or odd number that they are in the coefficient. Okay? Because the other part will be 0. So that's why inside, we are going to see later, we are only having 1, 3, 5. Okay? That's the coefficient that, or the n, that should be written down as a series. So the Maclaurin then start from this. We write everything as it is. This is x, and then adding again. Remember that we start the Maclaurin by taking this. This is n factorial x with power of n. Okay, this is how it looks like. So we expand this, taking n, increasing the n, and taking another part here, 3 factorial, and then maybe this is 4, and then plus dot dot dot, and this will result in the f0 is so every time we have the f0, the f double prime, or all the even number, including the when it is f0, this will be all 0. So the only way we have now is only the odd number n. Okay, so we have x, and here we're having the negative, right? Negative 1. So negative x cubed. Oh, I forgot the x. Sorry. Okay, and then if we imagine that there will be another 5, we're going to have another positive number, which is we take 5 factorial, and we are going to simply written down another negative, and then another positive, and so on and so forth. We have an alternating series, which we conclude that from here we can write our own in the series form. We could write taking n from 0, and since the first terms is positive, then I will just take this as n, because yeah, n equals 0 is just 1, right? And this will be the odd number, but factorial. And then the top equation will be the
x with power of 2n plus 1, the odd number. Okay. So this is how we get the sine x in Maclaurin series. Okay. Let me resize this so that it could be squeezed in here. Okay. Okay, this is for sine x. For cosine x, you could do the same thing. You can make this from cosine and then negative sine, negative cosine, and so on and so forth. Take 0 and then you get everything. And basically what you need to do is basically you put all into this pattern, into this pattern. And you will see in cosine, we are having the even number, not the odd. And another way to look at the cosine is we have sine, we can derive. So we can derive this sine, become cosine. And all things here will also derive. Or basically, we are going to derive the whole series. We can do that as well. So we can write here that since the cosine x is equal d dx sine x, which means that we are going to take everything from the sine okay, which this is resulting in 1. And this is 3x squared, but 3 is cancelled out. So we have x squared over 2 factorial plus 5 also cancels out, become 4 factorial. Okay. Or within this series forms, we get from n equals 0, this will in turns x with power of 2n, even number, and then this will be 2n factorial. So we get sine and cosine. Okay, now if you see the table, just a summary of what the basis for the regular, we call this the regular functions for the Maclaurin series. So we have 1 over 1 minus x, which we discussed a lot, right, at the beginning. And then we have e with power of x. This is quite, I think, one of the popular functions to be expanded. And then sine, cosine, which we did in the top. And we have the tangent inverse, also the log in the ln. Okay, so I hope you can also do the tangent inverse and then ln. You could take into the our expansion as we take the functions, the derivative, the second derivative, third derivative, take x equals 0, put everything inside, and then make into the expansion. I hope everyone can do that, okay? Because that is, I think, really helpful for the series. And another thing about the tangent inverse and the ln is that you could rewrite this from 1 over 1 minus x form, as I think I've mentioned this from previous. So you could relate the tangent inverse. You could relate the tangent inverse from 1 over 1 plus x squared, and ln from 1 over 1 plus x. Okay. You can relate this, derive integrations, you could do that. And basically, the result should be the same series. Well, if there is some differences, you can make sure that they have the same n. Okay. You could shift the n from 1 to whatever you want, but usually we take from 0 or 1. Okay, 0 or 1. That's the regular forms for the series. Okay, that's the Maclaurin. Okay, let me give you some cases and exercise. Okay, so let me start. Okay, I will just do really quick. So this will be the Maclaurin series. You have two functions, but I will just take only one. So whenever you have the x cosine x, what you can do is you can exchange the cosine with the series in the Maclaurin and then multiply with x. Okay? So basically, if we remember here from the previous part, let me just copy this. Okay? Let me just copy, or let me just write down the cosine x. We know in Maclaurin, the cosine x is that, right? And basically the x cosine x is basically we multiply x with this series. Which basically we can do that. So we can just bring x inside here and multiply with another x, which gives you the series. Which means we can do the same thing with the ln. So ln, the original series is from the ln 1 plus x. So what we can do is we can write, taking this, okay. Now we can exchange the x with the 3x squared. Okay. So for the 1 plus 3x squared, what we can do is basically we change every x with the 3x squared. Okay, basically that's it. Or if you want to simplify, this can be done. 3 with power of n, and then x with power of 2n over n. Okay. So this is simply how to write a new Maclaurin or Taylor series from the reference. So whenever you have a question like this, that you need to write off its Maclaurin series. You can imagine if you try to take, for example, this function x cosine x. You derive. You have like a many product rules, right? And when you put the x equals 0, you need to compute everything. Okay. So instead of doing that, I think the best way to approach this is we can take the cosine x because we know the cosine x is the series. Then we need to multiply this with x, which we can get this. Okay. The same thing with this. We know the ln 1 plus x, the reference. What we can do is we can exchange the x with 3x squared. We get the ln 1 plus 3x squared. Okay. So you can compare the two things. Okay. First, compare if you want to take the derivatives first, second, third, fourth, fifth, put everything in the pattern in the series, or you could do using the reference and then make some changes. Okay. So this is something that you can do and expected to do. Let me go for a while here. Another typical problem will be something like this. You have a typical series, and maybe you are going to be asked find the sum of the series. To begin this problem, we need to understand: is there anything that can be identified through the series? So if we see the series, we can see that it is alternating. So first we need to build our sigma notations. So perhaps because this is start from positive, negative, positive, we'll start with the positive. And if we would like to write this as a sum, if we start from n equal 1, this should be n minus 1 or n plus 1. This will be 1 over. We have n. And then the second part is 2 with power of 2 with power of 3, 4, etc. Or we can say this is 2 with power of n. Right? Now what's next? The next thing is how we can relate this. So basically, mostly, if we are going to have this kind of question, sum of the series, because we have learned the Maclaurin series, we know that, well, maybe we don't know, but we expected to know the reference from the table before. Then, what we need to do is actually, can we find some series that is actually the same form with those references? And then we can find, what we need to do is we exchange the variables inside. So this can be written as so I will bring 2 with power of n going up here, half with power of n, like that. Or let me put here, okay. Which this is very much aligned with this, right? Okay, same form, right? The difference is half, which means that we can first back this into the ln and exchange x with 1 over 2, which is giving you ln 3 over 2. Okay. So this is, we can write this as, so since we can write here the ln 1 plus x is equal then is equal, this is ln 1 plus 1 over 2 or ln 3 over 2. You can stop here, or if you want to calculate using calculators, you can get results. Okay. And by the way, for chapter 12 and 13, I will make some videos, short videos, maybe 2 or 3. It will serve as a resource, additional resources. So we are not officially learning class, but that will be just additional resources, okay? Because I believe the factors and factor functions, they will be needed for chapter 14, which is about the partial derivative. So whenever we finish the chapter 11, I will put the videos, and then we go for chapter 14. So the factors that I will include in the videos, introduction, I think it's very similar to what you have before, but I will emphasize on the dot product and the cross product, which in terms of engineering you will see a lot later. So if you want to review, we can review the dot product and the cross product in the factors. And then after that, also about the line of equations, the plane, which we are going to encounter in chapter 14 also. Okay. And in factor functions, basically they are the same calculus like in calculus 1, but the difference is they are in terms of factor. Maybe it is quite short chapter, so maybe only 1 or 2 videos that will for the chapter 13. So 12 about factors, 13 about factor functions. I will make as a short videos, maybe 3 or 4 videos that you need to watch beforehand. If you want to know the basis on the factors, and I think that it will be needed as a additional for chapter 14 and 15. Because in 14 and 15 we deal on multivariable calculus techniques. Okay. Now next example here. Yeah, I should be start from this one first. Okay. This the same as previous examples. What we need is we need to simplify it, and maybe if we look here, they are all in the power of n, so I will combine all together. And since the denominator has a factorials, this is similar to what we have in the EX. Which means that this will be equal to e with power of negative 2x. Okay. And aside from converting the series to function or from function to series, we can also use the series to evaluate the limit. Okay. For example, you have this limit. What we can do is basically we can exchange the functions. For example, we can exchange the e with power of x. So if we take this, so e with power of x, we can exchange by taking the series from 1 plus x 1 factorial. And plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 minus 1 minus x. This is x squared. So you see that this will be cancelled with this, and this will be cancelled with this. So we are left with the x squared, and if we cancel all x in the top, we can cancel this and this x, and we still have x squared, x cubed over here, right? which means that if we take the limit, taking the x equals 0, then we are going to have, let me write one more line here, just to give you sense that we still have half in the front here, and this is going to be all x. So this is x over 3 factorial plus, okay? And since from this n equal 3 is all 0, right? This is going to be 0, which gives you that this will be equal to half. Okay. But basically, you can do this with the L'Hopital rule that we have known already, right? This is just another way to solve limit. So we see that if we take 0 here, it's 0 over 0. 1 minus 1 is 0, 0 minus 0, 0, so 0 over 0. So we can basically take the derivative of the top equation, bottom equation. This is still the same, it's 0, it's negative 1. This is 2x. It's still 0 over 0. You derive again up until you get the 1 over 0. I hope you're still remembering the L'Hopital rule. Okay. Okay, one more example before we go to another practice. One more example. Okay, one more example. A typical question is finding the first 3 non-zero. For example, we have tangent x and the ex sine x. So if you know the EU of x and sine x, both are regular functions in terms of Maclaurin series, in the series. They both have the expansion, which means that you need to multiply and then see what term that comes at the first 3 terms, the 3 terms. And the tangent x is, we can get this from sine x over cosine x, which again, they are the regular functions for our Maclaurin series. Right? So basically, for example here, we can rewrite this as 1 plus, this is x 1 factorial, x squared 2 factorial, plus, let me just write everything, probably giving dot dot dot, and then the sign is x, alternating odd number, right? Okay, and basically we are going to multiply all of this. So basically we multiply, and then one by one we can see how it looks like and combine everything. I will skip some process. I hope you can just multiply as usual. So this will be x plus x squared plus you can try, okay? Because there will be some, we expect some subtractions because there are some negative signs, right? So we are expecting some subtractions. But don't write like really long. I think we expect to write maybe 3 to 4 terms. So we multiply this, multiply that, minus, right? And then multiply that also, and that. And we expect to have some subtractions, and this is how it turns out. And the same thing for the tangent x. This can be done from this sine over cosine, okay? Which basically we can write the expansions, each one of them. And the cosine is basically the derivative of the sine. And to get through the this divisions, you can take the long divisions. So this will be x power of 5, 120, these 5 factorials. And this will be 1 minus plus 4 factorial is 24, x power of 4. And basically you'd start taking 1 by 1, multiply x minus x squared over 2 plus x 5 over 24. Oh, this is cube. And you get everything here. And there will be some process, and you will see that we are going to get x plus 1 over 3 x cubed plus 2 over 15 x 5. And we can stop until here because we only need 3 terms. Yes, we need only 3 terms. So basically this is multiply 1 by 1. And do not write it too long. Maybe you only need this until 3 factorial, and then we subtract, we add and subtract. And do the same thing with this. You will get, so you need to subtract this first, you get the result, adding this, and then you get the result, and then adding this, get the result. And you can stop up until here. This is the 3 non-zero terms that we need. To stop here, and you can just say the first 3 non-zero will be x, 1 over 3 x cubed, 2 over 15 x power of 5. Okay, so basically that's it, the Maclaurin series. Okay. Okay, any questions? Any questions? If not, we can start some exercise. Okay, I think we can start some exercise. I have put here some of the from the chapter 11, the Taylor and Maclaurin series. So let me explain what kind of question that we expect. So the first one is actually using the reference, and then you can exchange as we did in the example. The second part is integration. So basically what we integrate is we integrate the series or the expansion of the series. And then after we integrate, we are getting the new pattern that we make a new sigma in sum. In some of the, I think some of the functions or the series, maybe I skip one of them, which is the binomial expression. I think this is, you can skip this one. This is binomial. But the other functions or series, I think we can we can find. The third one here is the first three non-zero terms, which we can find from multiplication or division. Okay. The fourth section here, this is how to take the series and then turns into function. So we need to do some simple algebra stuff here, just to make sure that it's matched with the reference, and then exchange the variable. And then the sum of the series is also similar, but we can get some exact expressions in numbers. Maybe I will try, maybe from all of this, maybe two or three first examples. I also prepare another exercise aside from this, which I think may be unneeded. Okay, I think the first sections should be okay, right? I mean, what you need to do is you take the reference. For example, the first one is the tangent inverse x, and then what you need to do is changing x with x squared. So you have the series, the sum, and then change the x with the x squared. Do the same thing with the other parts. Okay. But what I would like to emphasize maybe maybe 60, maybe. We start from 60. We have integrations of the x squared sine of x squared. So what is the step-by-step procedure? Okay, maybe after the break we can continue. Okay, so let's continue the practices. So try number 60. Okay, try number 60. So the basis for how to find the integrations. Remember that we have well, if you look at only the integrations, okay, if we use the normal integrations, I think we can substitute, right? We can just use substitutions. But in terms of the series, we can also do the so the first we can exchange this into series. So in terms of sum, and then we can take the integration with respect to x, which means you need to only integrate the x and ignore the n. And I think for some part of the functions, it will be maybe easier, okay, compared to the original one. But I think if you're already familiar with the integration technique, then you could proceed with the techniques on integrations. Okay. So this I will write as so let me write here number 60. So I will write from the reference that we need is sine x, which is we have done in the previous example. So this is supposed to be the odd number factorial. This will be the odd power for x. And then we exchange x with x squared, which gives exchange in the variable x. So we have x squared and then 2n plus 1. Okay. So this will be 4n plus 2. This is 2n plus 1 factorial. Okay. And then we multiply with the x squared. So multiply right here, right there. So basically we just need to add the power. So this will be x squared sine x squared is equal this is going to be plus 2, so 4, right? So this will be 4n plus 4. Okay. Now next is I will take this into our integrations. Oh wait. So let's integrate this. So let me write integrations with respect to dx, integration with respect to dx.
Okay. So we are going to integrate this with respect to x. So we only need to integrate this. We don't really care much about the n. Okay. So what we have here is the x with power of 4n plus 4, which if we integrate, this will be 4n plus 5, and don't forget we have the denominator is 4n plus 5.
So this will result in and don't forget you have a constant to add for the result of the integrations. So plus this will be sum and this is the infinite series for these integrations. Okay, so that's number 60. Now maybe we move to another example.
But from the right side, which one do you think we need to discuss? Any requests? So between 79 to 86. Any idea which part should we discuss? Any requests?
85, okay. 85. Okay. Maybe we move to the sum of the series. So number 85. So 85, we could play around first, see the series. Okay. Okay. Let me just write this question first. This is n, this is 5 with power of n. Now, it will be, I think it will be good if you know the reference, which one is the regular series or regular function that is in terms of Maclaurin series. But for some reason, maybe it's difficult to know which one is which, then maybe it's the best, maybe only 3 or 4 regular functions that can be easily remembered, like 1 over 1 minus x, that should be the easiest one, and then e to the power of x, and ln. As for the trigonometric like sine or cosine, it can be, you can proceed like we did, because sine or cosine, it has, the coefficient has 0, 1, or -1. So I think maybe in less than, maybe in several minutes, you can imagine the pattern immediately. Okay. And for tangent inverse and the ln, it will have some similarity. Okay? It will have some similarity that you can find the pattern from the series itself. Okay? But for this case, aside from playing with the reference, if we see that we have the power of n within this 3 and 5, we can rewrite this as 3 over 5 power of n over n, which we already discussed with these similar examples, right? Which is, this is going to be the ln. So remember that the ln 1 plus x is so basically we are going to exchange the x with 3 over 5. So we're going to get this 1 plus 3 over 5, or ln 8 over 5. By the same method, but different reference, number 86, if you see, it has the factorial. And the one that has factorial, and with the same patterns like this, is the exponent. So we get the 86 also can be done. This can be done by taking the sum and this is basically e with power of 3 over 5. So e to the x is okay, maybe just one more questions. Okay, from I think these two. 81 and 82, since they are very similar, and you could guess how we could proceed from that. Okay, look at number 82. Okay. We have x to the power of 2n plus 1. Here we have also 2n plus 1, but 2. So we can combine this together, right? So we can put these two over here, so this will be x over 2 with power of 2n plus 1. Okay? And we have 2n plus 1 factorial, which this is we have done in the previous examples. We have the odd number factorial. That this one should be sine, right? Should be sine. So this will be sine x over 2. And looking at the number 81, it's looking similar. It has odd number, but without factorial. These conditions will be for tangent inverse. Okay. So that I think that's the best way to see how to identify which one is the sine, which one is tangent inverse. They are looking similar, but the difference is this one is there is no factorial in the denominator. If you see any factorials, it could be sine, cosine, or the e. They all have factorials. And for sine and cosine, what you can take, the takeaway is the odd number or even number. You can guess which one is which. Okay. Like the 79, you have factorial x to the power 4n. This is the same thing as this one, right? We only exchange the x with 4. Okay. So as long as you can identify the regular functions, you can play around with this, and you can simplify it in more regular form, in a regular forms. Then you can identify the series into function, or from the functions into series. Okay. Okay, I will proceed to another exercises that I prepared. And hopefully we can finish. Okay, this is taken from some exam. Okay, which one is, I think maybe this one first. Let's take example here and try first, try your best. So there are 4 series. The question is asking about the which one is the convergent one. Okay, so first is we can check for all this 4. I think every time you have like you see the A and B, it has this trigonometry, right? It's trigonometry. And in fractions. And maybe sometimes it can be more adding some other number as well. But if we see any trigonometry, maybe the best way to start, maybe checking with the comparison test. Because we know that the sine or the cosine, and it has to be squared, which means that it's supposed to be only the positive, right? So this will the maximum is only 1, which giving you idea to compare with 1/2n, right? 1/2n, or just 1/n is okay, which is 1/n is diverge. And since this is between 0 and 1, this will be maybe some fraction here, which gives you the idea that this should be less than the 1/n. Oh, not less, greater, because of fractions. So we can start from the B, number B here. So since this diverge and this must be greater than the 1/2n, then this will be also diverge. So diverge, this is diverge. Diverge by, this is diverge by comparison test. And similarly, we can take this number A. So for number A, we could imagine the 1/4 with power of n, which we know this is, we can relate with the geometric series, right? We can relate with geometric series, which is, this is going to be, the ratio is 1/4, right? This is geometric ratio is less than 1. So we know that this is going to be converged. And the sine for n, this will always less, right? This is always or equal. And if we want to make sure this is confirmed, we can take the absolute value just to make sure that this is confirmed. Okay, so this is always the case. And since this is converged, then this will be also converged. So this is converged. Okay, now what's next? Let's take a look on D, okay, point D. Okay, if you have the fractions, but you see any square root, right? But you know that this is having negative. You can make this into another form that will be maybe better to simplify. So we can take the conjugations, its conjugations, we multiply, or we say rationalizing, we rationalize this to make the forms better for observations. So we can multiply this. Let me just write this first. So multiply with so this will be n plus 1, so minus and plus gone, and then this will be minus n. So it will be cancelled. So we only have 1 over n right?
And I think this is a better way to compare, because we have one, only a constant here, and we only need to observe this, right? And we can imagine that we have this squared n, and n. Well, we could say that perhaps if this is 2 squared of n, this is another n. So we have n squared of n, which means we can have a maximum. The dominant power here is n with power of 3 over 2. Okay, so we can see from this part.
Well, first maybe, let me just write this. This should be less than 1 over n, and then square root of n. This is square root of n, right? For sure, right? And this will be 1 over 2 and 3 over 2. So we can take this as a comparison. And since this is in terms of the P series, the 3 over 2 is greater than 1, right? So this will be converge series, right? Converge. And since this is less than this converge series, this will also converge. So this will be converge. Okay.
So sometimes, before we directly evaluate, if we see the form having some, maybe some forms like this, that we can maybe rationalize the forms, we can rationalize first. Okay? Because if you take this into your calculations, maybe you take the limit, or maybe you take the other method as well, it's very difficult to compare. So if you want to compare this one directly, it will be difficult because of the negative sign. It doesn't make assurance. But if we have this is easy to see that the denominator is always positive. This is all positive. So if we increase the n, it will be decreased as a sequence, right? As a series. Okay. Okay, so that one time first. The last one, the C, point C.
The point C, we can rewrite this. Okay. And then we can rewrite again by the property in the ln. We can rewrite as ln n minus 1 minus ln n. Okay. Which if you take
A few terms from n equal to, we are going to start with the ln1 minus ln2.
and it always getting increased. So this will be start. This will be ln 3 plus ln 3, which this is going to be increase a lot, and you will see that this is going to be, you will have 0, and then the last terms will be negative ln n, and if we take this as a limit, we still have these terms at the very end, right? Which is going to infinite, right? Which is this is going to be diverged. So the converge one is only A and D, so this is diverged. Okay. Okay, maybe maybe I will move to this one first. This one should be still warm, right? Still warm.
Can you do this? Try out while you still can, but because I'm not sure that you will try practicing by your own. Try it now, today. So you need to unleash your power of now. Because sometimes I know that the thing I've seen like generations because of the technology. You can get information easily from the social media, from the internet, and everything is easy and made possible. Sometimes you are easily to get distracted, right? You want to practice, but then you see your Instagram. Oh, this is cool. Blah, blah, blah. And then 10 minutes, 15 minutes, 30 minutes is gone without any efforts for study. But I think this is not because like what I want to say. It's not your fault because this is the world we live in. The only way we can succeed is we need to control ourselves. Then that's how I believe how we can conquer ourselves, conquer our, let's say, desire or anything that has implication within us. And that's how you start study. Because when you think study, I'm doing next, I'm doing this, I'm doing next. And then it's like day -1 for the exam. Oh, I haven't studied this. But you have many days for study. So management, like self-management is the key. And I hope in this period of time, this is the good way to have management. Like you need to manage, like maybe you have a hobby, you have like playful time also. Then you need to make it balanced, right? You have to make it balanced. Like you want to play game, okay, fine, that's fine. But you need to also think like at least the best way to study, according to some research, perhaps only 15 to 20 minutes. And then you need to take a break, and then another 15 minutes and 20 minutes. You can take the breaks maybe 1 hour, 2 hours. Because if you take all your brain into 1 hour learning or 2 hours without break, you will have a burnout situations, which will affect your mental health, and it's not good. So you need to make it balanced. You need to do also exercise. It's important to have your body in a healthy and good shape, right? So while you are in class, and if you have chances to try something new, just try it out. Although maybe you're thinking, oh, I don't know how to do that, blah, blah, blah.
But because you get so much access to YouTube, sometimes you just think, in my opinion, some student may be thinking, I can get this easily if I watch the tutorial in YouTube, which maybe is helpful, but again, when you have the time to watch the tutorial, the problem again is distraction, and you will keep getting procrastination. You keep delay, and then it's day -1 exam. Yeah, that's the reality of your life. Well, I also felt that way because sometimes I also get distracted. Okay, so the thing is, any interval of convergence, radius of convergence, the first thing is ratio test. Do the ratio test. What is ratio test? Ratio test is basically taking a comparison, take absolute value of your terms over your previous terms, right? And basically, we are going to exchange all the n with n+1. So this will be n+1 over n+1 cubed. And then multiply the n cubed over 5x minus 4 with power of n. Okay. Now you see that we can cancel this, and this is expected in most cases. This is expected. And then you have the forms should be 5x minus 4. And I will write the limit here just to give you the sense that we need to evaluate in limit forms. And approaching infinity of, let me change the color again. This will be n over n+1 cubed. Which gives you the limit. We can take this over n, over n, over n. This is 1, right? This is 1. So it will converge if this 5x minus 4 is less than 1. So you have a sense that we might have the interval now. So this will be so you will see that we have y is 4, should be 5. Should be 1 less than x. Not 1. 3 over 5, sorry. This is 1. Okay. But this is not complete, okay? Not yet. So let me write here, just to give you the notes, the ratio test. And the second is check the interval. So check when x is 3 over 5 and check when x is equal 1. How to check? Basically just put into your series. Okay? So when x is 3 over 5, the series becomes, so 3 over 5, if we put here, it will be 3 minus 4. which is -1, right? So we have -1 with power of n over n cubed. And we know that from this alternating series and also the 1 over n cubed, the p series, they are all converged, right? They are all converged. So this is converged. And when x equal 1, 5 minus 4 is just 1, right? So 1, basically this is just saying that this is going to be 1 over n cubed, which is converged. So we need to make the interval of convergence 3 over 5 equal 1. So this will be point D. Okay, that's the answer. Okay, so for next week, because Thursday is vacation, right? So next week, I will have another practice, but we need to jump to just introductory for chapter 14. For chapter 14, and I think we still have another Thursday, so we have 2 classes next week. So we can have like each classes, we have a 1-hour exercise for midterm preparation. I will review from chapter 10, 11, give you another set of questions, which hopefully you can check out by yourself. I have prepared, by the way, some of the questions in the notes. I will upload later. So this kind of questions, that this one, okay, conditional convergent, and also this, that part. Also here, okay. Interesting. Okay, and anyway, that's I think for today's class. But before we end, because end this class a little bit earlier, 10 minutes, because I prepared the feedback questions, which